Good morning, everyone. You can call me Locke. So today, I'm going to tell you the story of self-organized criticality. Well, I think you have started with the introduction on complex system. Complexity is something that very much in vogue today, where we try to understand the organized structure of the universe. Well, as a physicist, we study many things in the universe. The most famous one is the Big Bang, right? To understand that, we try to understand the four forces, the unification of the forces, and very much a reductionist type of thinking. But even if we understand all the forces, but could we understand how galaxies are made, how it is structured, and how life emerged in our planet? So this is the topic of self-organized criticality. And the story, in fact, starts with a quote by Victor Hugo. You may have known the play Les Miserables, where it says, who could ever calculate the path of a molecule? How do we know that the creation of the worlds are not determined by falling grains of sand? So here you see that there's a sand pile, a hand dripping little grain of sand down, and the pile start to form and start to emerge. Now this prediction or foresight by Victor Hugo, eventually, I do not know whether it inspired Purbach to came out with his theory of self-organized criticality, but the metaphor is very powerful. So I'm going to show you how that metaphor can provide a thinking model for you to understand complex system. Like any physical theory, it comes from inspiration of nature. So here itself, I show you the different scale in nature. So there's the astronomical scale, the largest scale in the universe, stars, galaxies, even the sun itself is full of intricate dynamics. Sunspots spewing out plasmas. If we go to our world, the Earth, you can see beauty everywhere. The clouds, the trees, the sceneries, memorable. Even the lightning itself. You will understand something about fractals later. You see the branching pattern. There's some sort of self-similarity. Finally, this doesn't happen just at the macroscopic scale. If you go down to the mesoscopic scale, you see diffusion, limited aggregation, fingering happen over there. And you can see also neuronal cells having this sort of self-similar feature. So this gives us some idea that nature has some pattern. And like all scientists, we try to develop physical laws from the pattern. Long time ago, we know that Copernicus, Kepler, and many of the ancient astronomers look at the skies and trying to understand how the stars move, and from there find pattern. And they came out empirical laws. From the empirical laws, we know that Newton developed his universal theory of gravitation. And the rest is history, right? So now, how then do we understand or explain complexity without coming from also a scientific basis? So later on, you will see that the pattern, the organized pattern that we see, would form the basis of some sort of empirical laws. And from that empirical laws, there is an initial version of a theory of complex system. So that is the motivation of my talk, to let you have a glimpse of such a theory. Okay? Now, before you can understand that theory, this is a lecture, so I need to start from the bottom up. So you need to learn some basics, okay? So to start with, the basic you're going to learn first will be this pattern that we call self-similarity. Now you look at this, road networks, leaf vascular network, river network. They look very similar, although they are from different things. What you observe in the pattern is that there seems to be similarity at different scales. You look at it, you zoom in, the same pattern emerge. This is also true for lung, for blood, for the neural networks. And these are diverse systems. It seems to not to be linked to each other. But yet, we see the same self-similar pattern. Could we characterize such a pattern? Just like in the early days when Kepler Kepler is one of them, who believed that the conic section, geometry, plays an important part in developing the theory of gravitation, right? So geometry is very important. So here itself, do we also have some sort of geometry that we can learn from? So the first thing we're going to learn today is fractals. So I'm going to give you a crash course on fractals. So I would need some interaction. Okay. I removed the slide because if you look at the slide, you know the answer. So there's nothing to learn. So I'm going to discuss how fractal is being calculated, something called fractional dimension, which is important for you to understand the later part of the lecture. So first, let me explain to you something that you may have learned so far. You know that a line, what's the dimension of a line? 1. What is the dimension of a square, for example? A plane, yeah. What's the dimension? 2. Yes, exactly. So later I'm going to show you a pattern that is called fractal. And your task is to calculate the dimension of that thing. But before I ask you to do that calculation, I show you how you get 1 for the line and 2 for the square. Okay? So first, we start with a line. Assume that the line has a length of 1. Okay? So this is a length of 1. The idea, remember, I told you, is about scaling. You scale the system, and then the thing is similar, right? So we scale it down by 2. So that is given by a number, r. I scale down by 2 means that I halve it. I zoom in. So I look at this part, you look at, this is similar to that. Okay? And by doing that, in fact, I have divided this line into how many pieces? Here itself is 2 pieces. So therefore, m is equal to 2. I can do it again. I can zoom it or scale down by 3. So this will form 1/3 each. And then how many pieces? That is 3 pieces. And the fractal dimension, d, is equal to log of m over log of r. So accept it first. Later you'll see the meaning. Okay? Then you see that this is log. Of course, I can keep scaling. By induction, you know that if this is r equal to n, m will be equal to n, right? So therefore, it's like log of n over log of n. So you see that it's equal to 1. So that's how you get 1 dimension. Okay? Now if I continue with a square. So this is, again, length of 1 on each side. Now we do the same thing. We scale it down by 2. What does it mean? It means that now the length is half. Okay? So if 1 becomes half, so I scale down, I zoom in. Again, you look at this small piece, is the same as the whole. Self-similar. So how many pieces here? 1, 2, 3, 4. I can again scale it down. And I can, of course, use 1/3. But to continue drawing here, I use... never mind, I should draw again. I use 1/3. So this will be this. So you see that, again, this is reminiscent of the whole. And this is 9 pieces. And you see that this is 3 squared. And you can keep doing this, right? And your dimension D will be log. If this is log M over log R, you can see that this is log. If this is going to be N, this will be N squared. So you can bring this down to 2 log N, and you see that this is equal to 2. Got it? So any question so far? So you know how to calculate fractal dimension. Okay? So now I'm going to construct something called the chord snowflake. And you're supposed to find its fractal dimension. If you can do it, I'm absolutely happy. If you can't do it, means that I have failed in my task. Okay? So first, what is a chord snowflake? It's the way you construct. First, you start with a line. Okay? Its length equal to 1. Again. The next construction is that we're going to take away the middle third and going to replace with something like this. So this is 1/3 in length. And then we're going to replace with this structure. This is also length of 1/3. And then, remember, we want to zoom in, right? We scale it. So we're going to scale it further by another 1/3. So here itself, this line is going to be divided. So here it becomes L equal to 1/9. Then I replace with this. I do the same thing for this part. Do the same thing for this part. And so on and so forth. I keep doing this until infinity. You will get a structure like a snowflake. Okay? So now our task is to find the fractal dimension of this. So remember that first we have a scaling, R. Now for this, what is the scaling, you think? What is R equal to? At first it's 1. We zoom in. So this part is a bit like that. You look at this. This is like the whole, right? Okay. This is supposed to be... So what do you think? What do you think is? 3. Good. What about M for this one? Remember that when I scale down, I count the pieces. I scale down, I count, in this case, the pieces. This is 1, I scale down, I count the pieces. I scale down, 4. Exactly. 4 pieces. Okay? What about this one? What is R for this case? With someone from this side. 9? Yes. Good. 9, right? You scale down by... How about M? 60. 16? You count, right? 1, 2, 3, 4. 4, but there are 4 of these. 4 by 4 is 16. You continue to see a pattern. Here will be 3 squared. Here will be 4 squared. You keep drawing, you'll see the next one will be 3 cubed, 4 cubed. You will propagate like this. So if I use the formula, D equal to log m over log r, if you go to some n construction, you have log 4 n over log 3n, right? You bring down the n, the n cancel. In fact, the cos snowflake happens when n goes to be infinity. So this n coming down is important. N is supposed to be very large, but it cancels. So what you have is log 4 over log 3, and you put in the calculator, it is approximately equal to 1.26. So the dimension is not 1, not 2, but somewhere in between 1.26. It's a fractional dimension, so it's a fractal because of this. One interesting thing about this fractal is that what is its length? Very easy to calculate. You see at this stage, the length is 1/3, 1/3, 1/3, 1/3 is 4/3. The length of the snowflake is 4/3 here. The length here, in fact, you calculate 16 of this, and each of them 1/9, so it's 16/9. So you see that this is just 4/3 square. And you can imagine that at the cos snowflake, you'll be 4/3 to the power of n. So the length at the cos snowflake, 4/3 to the power of n. And n goes to infinity, which is a cos snowflake. This is going to go to infinity. So the length of a cos snowflake is infinity. This is the important concept. Why? What is the length of a one-dimensional line? It is always 1. What is the length of a square? When I say length of the square, it's not the perimeter. It is as if you take a string and you go around and cover the square surface. And you can imagine that it's going to be infinite. So the length of a square is like infinity. So here itself, you have something like 1 dimension, but infinite length is something like a square on the right-hand side, but it's something like a line on the left-hand side. So you see, give you some intuitive feeling about this object, a fractal of dimension 1.26. So this is what it is. You go further down, you see that it looks more and more like a snowflake. And such a pattern looks more like nature in some sense, right? So this is geometry by Mandelbrot. There's a book by him. It's about nature being fractal. It's good to read it, but let me progress. Now, look at this. I give you the dimension, the definition of fractal. D is equal to log of m and log of r. You can then convert it back. It's equal to m equal to r to the power of d. You take the logarithm of both sides of the top, you get the one at the bottom. The important thing about the equation here is that this is a power law. It's a power law. The power exponent here is the fractal dimension. And now I link to the motivation. The motivation is that we see pattern in nature. We want to understand the pattern. And interestingly, this pattern exhibits power law. So here I show you power law distribution of different things. You have the ranking of cities. So the y-axis relates to the size of the city based on the population. And you can see that there are many cities of small size, but few cities of large size. So if you plot the distribution, you get something like a straight line in the log-log plot with the gradient being like the exponent. You can do the same thing for words. You take the novel. You rank the words. The most frequent word, in fact, is the, T-H-E. It appears very frequently in novels. And then you rank it accordingly. And you plot the distribution. Again, it's a power law. Interesting. You take Bible, you take any other laws. You form a power law. Happen in X-ray intensity, pulsar glitches, biological extinction, which I'm going to talk about later. Cotton price. You take the price of a cotton, variation month by month, you plot the variation, and then you find that large variation is less frequent than small variation, and it follows the power law. Earthquake magnitude, the Gutenberg Richter scale, the famous one. Large earthquake is less frequent than smaller earthquakes, and it follows the power law. Of course, sometimes we try to give meaning to the power law. Maybe it's some sort of process. The interesting case is the ranking of words. We think that, oh, there must be some interesting things about human typing that give rise to the power law. There's an example by Miller. You take a monkey, and then let the monkey type on the keyboard. After that, each character is independent of the other. Of course, there's a space. You can press a space. So that space would tell you the words, right? And then you rank the words typed by the monkey. It's also a power law. So you need to be careful when you interpret power law. And there's another important feature. There's 1 over F noise. Very much in the world. So the intensity of light from quasar, which is an astronomical object, the global temperature variation. Now, what is 1 over F noise? 1 over F noise is such that it's like, now there is self-similarity in the pattern in time. You can see small feature and large feature. That, in other words, you see 1 over F is like a power law, right? F to the power of minus 1. Okay? So it's like small frequency is more frequent than large frequency. And this frequency distribution gives rise to some sort of self-similar pattern in time. And interesting thing is that 1 over F noise lies between the boring case of a tone, a single tone, or white noise, which is the hiss you hear from television. And many people believe that 1 over F noise is like a complex system, because you see music itself follow 1 over F noise. So music is something that of us would think that is something pretty complex because it surprises you, right? That's why you like to listen. You try to listen to the next tune that is something that is unusual, okay? But many things, vacuum tube, semiconductor, heart, so many things have this 1 over F noise. So these are empirical facts. And how do we then think of a way to come up with a theory? There is a theory that has power law behavior. This theory is in physics, in statistical mechanics. It's related to phase transition. It's well studied. There are very good examples. Here I show 2 examples. One is the one that relates to phase transition of the liquid gas. You must be aware of this because you boil water, right? You boil water, see that the water is at the liquid phase. You increase the temperature, it becomes a gas. So there is a change in density. Now, the change in density can be plotted like a sort of phase diagram. So here itself, you have the pressure. Pressure is a y-axis and the density. And then you can plot. So you can see that there is some boundary relating to 2 different regions. Now, what I didn't plot here is that now such a phase transition between liquid and gas is what you call the first order phase transition. First order phase transition, you do not see power law behavior. But there is a second order phase transition called the critical point, where it exists also for the liquid gas. At this point, actually, you cannot really differentiate the difference between the liquid and the gas. They look very similar. But there exists such a point. Another system that very famous exhibiting it is the Ising model. I'm going to talk about the Ising model, and that will be the example I'm going to use. And there's a critical point in the temperature. At that Curie temperature, we call it, if you go above the Curie temperature, the ferromagnets, the one that you use, you might like your electromagnet or whatever. If you heat it up a lot, you lost its magnetism, right? It doesn't work. You do it in your high school. But if you don't heat it up, and then you let it go, after some, you magnetize it, right? And you realize that, oh, it can be used. Even iron, right? A paper clip, you can make it magnetized. So there's a transition from being magnetic to non-magnetic if you change the temperature, you heat it up. Now that point of the transition is called the Curie temperature. I'm going to talk more about it. But at that point of the Curie temperature, there is this thing called the second order phase transition. And at that second order phase transition, they have found power law. And this is real because they measure it experimentally. Here itself is for the liquid gas, here itself for the ferromagnet. You can see that these are numbers relating to the exponent. And here I'm going to show you the Ising model to make it clearer. Ising model is a theory for the ferromagnet that I told you, the paper clip where you magnetize it. The model consists of lattice, two-dimensional lattice, where each side, you can think of it like spin. Like this is the magnetic, small little magnet. You point upwards is the north up, or you point down, which is the north down. So each magnet actually interact with its neighbors. So it's this term represents the interaction. Here itself, you may exert the external field. So the field is up, then everyone tend to align up. Field down, everything align down. So, well, the interesting thing about this Ising model can be also explained when we switch off this field. Let's do that. We switch off this field. Okay? So there's imagine that there's ferromagnetic domain inside there. Okay? So if the temperature is very large, these are the spin. The black represent, say, up, white represent down. You see that it's just random. You take the average, you don't see any bias direction. So that's the reason why you could not use it to lift any other magnetic material, iron material. If you bring the temperature to very low, to 0, now this term here is going to dominate. This term here is the interaction between the neighbors. So now that depends on luck at the moment. So when you go down, some domain is more dominant. Everyone start to follow that, like the majority. Okay? Then everyone start to flip up. Okay? So when you flip up, then you see that the black is dominating than the rest because this term dominates. Like fashion. Okay? Everybody using MacBook? No. This class is different. Sometimes I look everywhere is MacBook. So I thought it's like everyone spin to that. Okay? So it's something like that. Now, the main mechanism is the competition between two things. This and temperature, which is the heat. Okay? There are two things. So if there's no heat, everybody will just bias depend on the majority. If there's heat, then things become randomized. Now, there's a sweet spot where the competition, some sort of balance. Now, this sweet spot is the part that happened at the Curie temperature. Okay? At this spot is the spot of complexity. So this part is very important. Okay? So this is the part where you will appreciate complexity. Why? Because at this sweet spot, you want to align, but you are also disturbed by the noise. Okay? But you are not distracted by the noise so much as to become like this, because you are also very much disturbed by the fact that your neighbors is aligned in a certain direction. Okay, so therefore, you see these patches. These patches is there. Okay, so big patches appear with small patches. And you can see a signature of this power law because you have distribution of big patches and small patches. And these patches is not always there. You can disappear because this is the noise would destroy this. So this whole thing is dynamic. So at this point you appear, then after that you can disappear, but the big patches will appear somewhere else. Okay? So it's a random happening. But the random happening would consist of these big and small patches, and you calculate the distribution of this. It's like a power law. And there's correlation length spanning the whole lattice. So something that is here is correlated with something that's there. Okay, so this correlation is statistical. And things keep changing. It's very fluid. So this is the part, the sweet spot where we have complexity, the power law behavior. And if you like, you can try to simulate the Ising model and tune it and look at the evolution. It's going to be beautiful, so you should try it. Okay? And there's another important fact about critical transition. Very important. You look at this. There's manganese fluoride and iron. These are two different materials. They have the same, almost the same exponent. In fact, this one also about the same. And this is for the specific heat. And now is for the spontaneous magnetization. They also find the scaling. Manganese fluoride and iron, you see, is about the same. And some others as well. Now, this is the concept of universality in critical transition. It means that different things can exhibit the same behavior, the same power law behavior. So therefore, if you can understand something maybe in the biology case, you may understand something in the social case. I'm making some examples relating to complexity. So therefore, you can study one system and use that system to understand another system. So this is a very powerful concept because it allows the theory of critical transition to be applied to different systems. Okay, so you learn from something, you can port it to something else. And this is another concept of complexity. Here, the x-axis is the order parameter. You can think of it like, this is like the Ising model where you have the frozen state. Everyone aligned upwards, temperature T equal to 0. This part here is the high temperature state, very noisy. These two ends, the complexity is near to 0. Why? Because when that frozen state itself is so simple, right? You can understand it, predict it, okay? And what about the one, like the noisy one? In fact, it may things to be difficult. You cannot predict. But in fact, you realize that physicists develop a branch of statistical mechanics. You can use statistics to make prediction. So in fact, it is statistically simple at the end. So the gas molecule around the room is simple. Why? Because you look at this part of the gas going around and that part of the gas going around in the space is the same statistically. No different. In the case of, for example, your ideal gas, right? It's simple. That's why you can analyze it. So the two ends, it is very low complexity. But in between, like for example, at the Curie temperature, now that is the part where organization happens. And in fact, we can't even write equations for it very much. We are lucky to have power laws, right? So that part itself is complex. It's the age of chaos, somebody call it. but it is a part that is of great complexity. Okay, I spent about 35 minutes providing the motivation. So now here comes the topic of today, which is self-organized criticality. With that background, Purbach, okay, trying to understand all the empirical laws observed in diverse systems, he came up with a theory. He made use of the then understanding of critical transition in statistical mechanics, but he put in a very, very important element, which is the element of self-organization. Remember just now when we talked about the Ising model, you want to reach the complexity stage of Curie temperature, right? What you do is that you need to tune the temperature, right? You need to adjust the temperature until Curie temperature. The system is complex. But the idea of Purbach is very ambitious. He's saying that you do not need to tune. The system will self-organize itself to that state of the critical state. It will self-organize to a complex state. That's the idea. He has a way to show how the system can self-organize itself to that complex state. Okay? So let me show you his thinking. So he starts, like all scientists, he starts with some initial idea. The first idea he starts with is the coupled pendulum. This pendulum can rotate 360 degrees. Imagine that you have one of the pendulum, you wind it up. And this pendulum actually is coupled to many along the line. So you wind 1, 2, 3, 4, and so on and so forth. Now, when you wind a pendulum up to this state, you know that this is unstable, right? You touch it a bit, you will rotate. Now, you have wind many of these, then of course, some of them is down, some of them is up, but this would cause something like an avalanche. So this go down, you will, because of the coupling, you cause the other one to go down, and there's some sort of avalanche happen. So he started the idea with this coupled pendulum. But this is very difficult to analyze. And of course, he analyzed it and got some power law, but he thinks that there should be an easier way to visualize. So that is the paradigm of the sand pile. He realized later that a better model or better way to think about the idea of self-organized criticality is the sand pile, with his collaborator, Chow Tang and Kurt Winterfield. So how does it work? Best is shown by an example. So here is the model, a lattice, and numbers on the lattice represent grains of sand. 3 grains of sand, 2 grains of sand, 0, no grains at all. Now, remember that just now the pendulum, there's a state of instability, right? So here itself, there's a number here that is the threshold, the number 3, okay? It is just below the instability. What happens is that now you add 1 sand to this, that is, at this point, 1 sand, 3 would become 4. 4 is unstable, like the pendulum. Then what happened? Then it will topple. When it topple, the sand here will be given to these neighbors. So this will increase to 2, 2, 4, 3. 4 sand each to its neighbors. And of course, itself becomes 0. Now, when that happens, you see this is also just below threshold. Then now this becomes unstable. And it will topple in the next time step. And finally, it becomes this. And then, of course, it stops because there's no instability in the system. So that's it. This is his model. Each of these, when it topples, is like an avalanche. Okay? So let me show you something about this avalanche again. So here itself we have 4 by dropping a sand there, and this would topple into this side. So now here you have two unstable points. And you know that you can topple next. So of course you ask a question. The next thing, should I topple this first or topple this, right? Answer is it doesn't matter. Okay, I'm going to show you that both give the same result. So if we topple that one first, this is what you get. Okay, then after that you would topple the one over there. And this is the result. Now if we continue to topple that one first, this is what you get. And this is the result. You look at these two, they are the same. Now then you need to do something. We need to define something, because now I just show you an example. Pearl-Buck actually do a lot of simulation on this. So from this, he going to measure something, what you call the size of the toppling, like the size of the avalanche, and also the time in which the avalanche goes and then stop. And with that, he's going to plot a distribution. So a size of an avalanche is like, now you see here itself you have one toppling, and there's another toppling here and another toppling here. There's the 3 toppling, right? So the size of the avalanche is like 3. Or say toppling event is 3. Of the size of the toppling is 3. But the size of the avalanche is this one. So there's another one called the size of the avalanche. The time of the avalanche is 1, 2. So this one is parallel. So here itself we do it sequentially, right? But actually when it topples, it counts as parallel. Okay? So there were 1 is together and 3. So the length is 3. So with that, he plot the distribution. And the distribution, in fact, is a power law. And this is for the cluster size or the lifetime. So this is for the time. So this is for 2 by 2 lattice. This is for 3 by 3 lattice. So we got power law. So now what is the meaning behind this? Okay. Now, first, this self-organized model have some interesting feature. First, now when you drop a sand, at first there's no instability, so everything would just, nothing happen, right? Until there's a instability, then you topple. Okay? So you need to keep doing this. Or maybe I should give you another metaphor. So a better metaphor, in fact is the sand pile. Okay? So in the case of the sand pile, remember you keep dropping sand. At first you drop, it's just a flat pile, nothing interesting. But as you keep dropping, you will start to form a pile. Okay, you drop at the center, you keep accumulating. Until a certain stage, we call the critical state, okay, or the attractor, in fact. At this state, if you drop one sand, this would start to avalanche. Okay, then you will settle. Okay, you will settle. But then now if you drop again, it would again avalanche. So you realize that there is a critical slope. Before the critical slope, you drop anything, it is nothing happen. But once you reach a critical slope, you drop, you may have a small avalanche, but sometimes you drop, you would have a large avalanche. So therefore, in the same case of the sand pile model on the lattice, you keep dropping at first, if everything is 0, of course you have 1, 2, whatever, nothing happen. But reach a certain stage that you will have, that's what we call the attractor. So at that state, you drop one, avalanche. Drop another one, maybe big avalanche. Okay? So it is like that sand pile reaching a critical slope. So therefore, this is a very important idea, is that the system itself reach a critical state. That's a stationary state shown on the top left, top right corner of the diagram. And then it will just, these are like example of the evolution of the state, and finally it reach attractor. That is the region where you will see avalanches, and you will see power law behavior. And of course, they also see 1/f behavior and fractals. So you all link up with the empirical work that was found. Okay, so this is very important. This idea of the attractor of the metastable configurations. Why? Because sometimes nowadays they say that the brain, the most recent research is that the brain works in as a SOC. So when you are now with me, some of you may be in that state. So you have ideas coming out. Some of you are very sleepy or whatever. You are not actually in the critical state. So I go to drive you sometimes to your critical state, and you see fluctuation happen in avalanches, ideas come. Okay? So something like that. It's very important, the stationary state. Now, there's another aspect of it, because later on, if you do research on power law, you will see your plot pictures like this. You will see that, well, there's power law only in limited region. It's like just this part, and it just drop off. So what does that mean? Of course, you know that power law comes from scaling, right? You look at a small part of the avalanche, it's the same as a big part of the avalanche. And you hope to see bigger avalanche. But can you see bigger and bigger avalanche? There's a limit, because the lattice, you can only simulate this size. You want to see avalanche bigger than the lattice? No way, right? So therefore, those are what you call the finiteness, because we cannot. Just like you see scaling in coastlines. You see that there's scaling. But then, finally, the limit of the thing is that the size of that island. You cannot go beyond that, okay? So it's the upper limit and the smallest limit, because you want to go to see things as small as possible, right? But at the end, the smallest thing is the molecule. You cannot go below that. So there's an upper cutoff and a lower cutoff. That's the thing. So you need to be careful when you see this. So therefore, each of these means that we use larger and larger lattice to simulate it. So you see the cutoff just shift to the right. And the nice thing is that they can do some sort of data collapse. Because in physics, in the case of statistical mechanics of the critical transition, right, the one that I told you, Ising model, they found that it can all be scaled like this. So this part itself takes care of the cutoff. In fact, the cutoff also follows some scaling law. So this is the D resulting of the cutoff, and tau resulting of the cutoff. The theory is very well developed. You need to use renormalization group to analyze such a thing. But too advanced, I won't go into it. But if you are interested, then read the literature on that. Okay, so let me summarize the feature of the SOC. So first, there's a slow drive. Now, when we put the sand, the sand is an external drive, and we do it slowly. We drop it, and we wait. The avalanche happens, and then it settles down. That's a fast relaxation. Before we put the next one, we don't, during the avalanche, put the next sand. Okay, we wait until we finish, relax, then we put the next one. So this is the slow drive, fast relaxation. Open means externally drop. That's why it's an open system, not a closed system. And then it drops out. Okay. Dissipative. Well, sometimes we can drop, and then instead of giving 4, we can give less. So the grain can disappear. Okay. I'm going to show you one model later. Threshold. There's a threshold, right? 3 just now. Above is instability. There's history. When you drop, the avalanche happen. In fact, you can mark that particular sand, and then you trace the history of the evolution. And avalanche fluctuations. You can see that there's fluctuations happening. And of course, I show you the metaphorical sand pile. And they have done experiment on real sand. One is used rotating drum by University of Chicago. Unfortunately, they did not find the same power law because the sand itself has inertia. So therefore, when you roll, you reach some critical slope, like what I've shown you. Then after that, because the sand, when it falls, there's momentum. So one whole sand will just go with it. So then there's some oscillation. So we try on that, it doesn't work. We try on IBM experiment, they try on a plate, dropping sand, like the way I show it. At that time, they don't have no video doing it, so they also seen some oscillation. Later, they use videos. They use videos to do the sand pile experiment. Similar things happen. They could not really get a very nice power law. So the conclusion at that time is that real sand pile doesn't follow the power law like the way Purbach described it. But the interesting thing is that the rice pile works. Rice, you take the long grain version. Long grain, not the round one. The round one also doesn't work. Long grain, as it drops, because it breaks the inertia. You will not, each one will tangle each other. So therefore, you will not like push the whole thing down. So therefore, you jam it, and it describes exactly the same assumption used in the model. And the Norwegian rice pile follow the power law. So one of the important model or application of SOC is the earthquake. So I got to show you this for sure. I'm going to, within the next 10 minutes, going to show how the application of SOC to diverse system in a pretty quick way. So you got to follow me a bit, okay? So here itself is an earthquake. Earthquake is fault. You know that the fault line, tectonic plates, move against each other. Then you will reach a critical state, and then it relaxes. And you have the famous Gutenberg-Richter law. And they can use this model to describe it. And it's a homogeneous driving. It's not one sand going, but one energy term going simultaneously everywhere, simultaneously. And they do that, and that is based on this moving plate model, and they found power law, right? So it's a way of verifying that the idea works and explain the Gutenberg-Richter law. Another interesting thing is biological evolution. In this case, it's co-evolution. What happened is that they found that there is punctuated equilibrium in species. Here itself is like, for example, long time ago, there's a lot of species go extinct. Suddenly, large extinction event. Dinosaurs dies away. But there are also very small little extinction event. So you plot this extinction event, it follows power law. But how could you actually understand the fact that biological extinction actually happened? And it happened sporadically, not like what Darwin says is gradual. Nothing happened, suddenly some small extinction or some large extinction. So an interesting model is this one. It's the Bach-Snepen model. The idea is this: species interact with each other. So for example, we understand species as their fitness. A frog is fit, but then it can evolve to fitter by having a more sticky tongue. Of course, then bad news for the mosquito. A lot of mosquito will die and would extinct. But then mosquito can mutate, and it become more slippery. And now, more difficult for the frog to eat the mosquito. So at first, one have a better advantage than the other, and the other one mutate, and now everything becomes the same. This is what we call the Red Queen effect. It means that you try to run ahead, but because the floor is also moving, so finally you finish the race, you see, I'm still at the same spot. Okay, so the frog and the mosquito at the end of their evolution seem to be at the same spot. So it's like some sort of what they call evolutionary stable state. That doesn't seem to explain the punctuated equilibrium. But Bach-Snepen came up with this model, very simple model. Random numbers between 0 and 1 are arranged in a circle at each time step. So you range random number between 0 and 1, and then look for the lowest number. You're going to eliminate that, just like you extinct that species. But you not only extinct the species and its neighbors as well. This is like because they are interacting. So that's like the frog and the mosquito, and then the one that eat the frog. Okay? So when you mutate something, you affect also its neighbors, and then you change randomly those numbers, and then you evolve it. Then you see that you always take the lowest number to do it, although it's random. So you see that the lowest number actually keep increasing until some threshold, and here itself is now the critical state. So everything above here, of course, those largest ones will not be chosen. Now, those that is chosen will be right at the edge of the threshold because those are the lowest number. You choose it, you replace it with some random number. It could be then lower than the threshold, then it causes avalanche. It's like the mutation cause some event. So now the system, the species try to interact each other and extinct and survive, and then finally it will go back to the top. So these are like avalanches. So what happens is that these are like the punctuated equilibrium. So nothing happened if nothing drop out. So it's like the devil's staircase here, nothing happened here, but suddenly something happened, then it goes up with the avalanches, and then go on. So therefore it explains what we call those explosion of species being dead or alive. Next, I'd like to talk about how you use complex system thinking in one system on another. One of them is a forest fire. Forest fire is another type of model of SOC. Okay, so you have a cell with burning trees, when it turning into empty cell, and then a tree will burn if at least one neighbor is burning. A tree ignites with probability F even if no neighbor is burning. A tree appears in an empty cell with probability P. So therefore, empty cell, some tree appear with probability P is like growth. Then this group is growing. Then after that, as it's growing, then you have some probability of igniting it, and after that you will burn if your neighbor to it. Okay, so you have a power law. Now the idea here is that the real forests follow this. They found that in the paper in Science, the real forests actually follow such a power law. So therefore, in the Yellowstone effect, at first they did not burn the tree. Means that they let the tree be what it is and avoid burning the tree. The tree grow very large. So suddenly lightning come. Then the forest is very big because you burn everything. So that is a large event. And they realized that the best way to manage it, in fact, is to constantly, normally, routinely burn trees so that you don't have large patches. So you have some medium, at the end of the small burning of the medium patches, right? So when next time the lightning comes, you do not have a situation where large part of the tree is being burned, right? So that is something they understood, and they use it. And we realize that this happened also in the case of riots. You don't let the emotion become so huge that when something happens, ignite, then the big riot comes. So the way to manage is that before that, you already burn it. I mean, you go and ignite it. Small one. So that the big one would happen. So that's the idea. So this is something we learned from forest fire to managing complexity. Okay, there's stock market crashes. Same idea. You can, all these things can self-organize to some critical state, speculative bubbles, and then it crash. I don't want to talk too much. I have just 2 minutes. Brain, I already tell you just now, right? You are sleepy, subcritical. You are overwhelmed, you're supercritical. There is a critical part where you can think clearly, okay? Same for traffic jam. The critical state with jams of all sizes is the most efficient state. So free flow actually is underutilizing the road. You jam, of course, overutilization. Now there's a sweet spot also, where it's almost congested, but cars are still moving. That's the SOC state. In fact, they show it, and there's also a power law, okay? So now we have a relook of SOC. So it's slowly driven, interaction-dominated threshold system. Self-organization versus tuning of parameters is robust. In fact, they try different things, same power law. You can analyze it by means of different theory. So I'm not going to talk about much about this. Now, important is that there's a fluctuation mechanism. And fluctuations have prevented us from predicting SOC system in detail. Understanding mechanism is important. So these are something I just told you. So you release it. The last slide. Now, when you see power law, don't always think that it is due to SOC. It could be okay. It could be some other things. So it could be variable selection. It could be due to the variables. There's like power law like. Gilbert's law means rich get richer type of mechanism. Coherent noise model and highly optimized tolerance. These are very special model, not in critical state, but yet still power law and heavy tail. In fact, in the next lecture is the best time for me to introduce. Professor Turner is going to show you another way we have power law behavior, a beautiful way, okay? And yeah, so when you also plot power law, many of the distributions look like power law, like log normal, log Cauchy, and so on and so forth. So therefore, don't just conclude that it is power law. There's a very rigorous algorithm by Closet and Newman that use some maximum likelihood estimate to see the goodness of fit. So do those things. Don't just claim that it's power law, right? Okay. And yeah, sometimes there are events that is not just fit to a power law, like Dragon Kings. Okay, so with that, I finish. So thank you very much for attention.